So let's just finish this off with a couple of questions. So the first question that we're going to start with is finding the amount of protons and neutrons in sulfur 32 and iodine 131. So you'll need a periodic table to do this. You can just look one up on Google if you don't have a physical one. But it's pretty simple. The best way to do this is to kind of draw out a chart for yourself. So I already drew it here, but you can write this down on your paper. You have your atomic mass in the first, your atomic number in the second, protons, neutrons. This is what we're trying to find here and here. So we can go to 32S, which is going to be, or sulfur, on your periodic table, which is number 16. So we got two answers right here already. You just have to be able to read your periodic table. So 16 is our Z. Let me use it for public so you guys can see the answers. 16 is our Z. It's the top number on your periodic, or on your little element. And underneath it is the atomic weight. And that's our A. So it's 32.07. And what we can do is our protons is going to be equal to Z. So protons is 16. And then we're going to subtract 16 from here, because this is the exact isotope number that we have. So 32 minus 16, put it in your calculator if you can't do that in your head. If you can, you know it's 16.
I can't.
And then you'll have it. So your neutrons are 16, your protons are 16. Your A is 32.07. Now, if we wanted to find the amount of neutrons in just the average of what it is, you can just subtract 32.07 or 16 from 32.07, because like we know, A is equal to P plus N. This is a very powerful formula for these kinds of questions. Now we can go to iodine. Okay, so now we're going to find all these things for 131 iodine. And what we can do is, again, look on your periodic table. So we have here that iodine is number 53. So our Z is inherently going to be 53. Our A, which is the atomic mass, is going to be 126.9. And then what we can do is that we know protons are 53 because it remains the same for your Z to your P. And then what we can do is we're not going to use this number. So the reason I write these here is just to remember, don't look on your periodic table for these. Look here, because this is a different value than this. And that is because this is a different isotope of iodine. Rather than, well, it might be the most abundant, but it's probably not, because the average is nearly 127, which is about 4 values less than 131. So what we can do to find the neutrons is 131 minus 53. You can do that on your calculator. I'm going to do it because I can't do that in my head. So it's 131 minus 53. That's going to get you 78. So there are 78 neutrons. And there you have it. It's not that difficult. There's really nothing to it. You just subtract your protons from your isotope value and you get your neutrons. Pretty easy. Okay, so now let's go on to another question. We are trying to find what is A. Now, in case you don't remember, A is atomic mass. So we're trying to find it for strontium, and we're given that 87 strontium occurs 40% and 88 strontium occurs 60%. So how we're going to do this is remember that atomic mass is just the average number of the isotopes occurring. So what we can do it's pretty simple. You're going to take 87, which is the weight, and multiply it by 0.4, and you're going to add that to 88 times 0.6, because these are the percentages, these are the values, they're corresponding. When you add these two together, it's going to give us the average of that. So it's not like taking an average where everything is equal to each other, it's just taking an average where things are not equal to each other. So plug that into your calculator, unless you can somehow do 87 times 0.4 in your head. And we're gonna get that it is equal to 87.6. Now, what we can do is actually check on your periodic table what is the atomic mass of strontium. So strontium is number 38. We were right, 87.62 on here. And this is an AMU, atomic mass unit. And that's pretty much it. It's not that difficult. Things do get more complicated with more isotopes, but we'll get into that more when we get into mass spectrometry. Okay, so now we're on to our last question of this section. So we're going to be trying to find the percent natural abundance of copper, of 63 copper and 65 copper. Now we're given the exact values of 63 and 65 copper, and we're also given on our periodic table, but also in the problem, the tabulated weight of, or mass of copper. So if you look on your periodic table, it's going to be number 29, and it is 6355.55. Here it's a little bit more specific, which is great because we have quite a few more sig figs to work with here. So how we can do this is similar to the last problem, in which that we're going to use a variable to find the values of the percentages. So like how last time, let's give ourselves a little more space. We got 62.9298. Instead of putting a percent here, we're going to put X. And then we're going to put plus 64. I'm gonna run out of room. 9278. Now we're gonna do 1 minus X on here because we know that 65 copper is greater than the value of the tabulated copper atomic mass. So we know that it's gonna be 1 minus the X because there's gonna be less of it, since the 63 is factoring way more into it. As we can see here, 63.546. So put 1 minus X on the weight that is furthest from the tabulated atomic mass. And we can set this all equal to our value here, 63.546. Okay, so now you just solve this like algebraic equations. So we're going to get 62.9298x, and then we factor it out to here, factor it out to there. You're going to get plus 64.9278 minus 64.9278. And now, X. Do not forget that. Definitely do not forget that. Now we can simplify this side of the equation by subtracting we can subtract 62.9298 and 64.9278. So that's going to get us minus 1.988x. And again, keeping that 64.9278. You can write it on the other side as a plus. It looks simpler to me to do it this way. And then what we can do from here is move all of our constants to one side and our variables to the other. So I'm going to move this one over here and that one over there, so that way both sides are positive. And that's gonna get us 1.3818 is equal to 1.988x. So now we have that 1.3818 is equal to 1.988x. So this is going to be for this value here, or x. And then over here, I already factored it out, but pretty much what you would do is I'll just draw an arrow so you can see, 1.988 times 1 minus x. And so I already factored it out, or not factored it out, but like factored it back in, pretty much. And I got 1.988 minus 1.988x, and it's a little squished over there. So when you solve these, like basic algebra, you just divide 1.988, and we get x is equal to 0.6916, and x over here is going to be equal to, so again you subtract 1.3818 minus 1.988, divide that value by negative 1.988x, you're left with your x, and you get 0.3084. Now to convert these into percentages, you just multiply times 100 times 100, and you move the decimal place over 1, 2. I think most people know how to do this part. And you get 69.16% is the percent natural abundance of 63 copper. And we get that 30.84% is the natural abundance of 65 copper. So that's pretty much it. This one is a little bit more complicated, but trust me, it'll get more complicated with mass spectrometry.